Everyone. So today we're going to discuss a bit about complexity and different complexity measures. There are actually dozens of complexity measures, so we will just mention some of them. And just as a refresher, last class we saw Markov chains and decision processes and games, and also the equivalence when we don't have full information. And we also saw how we can measure the entropy rates of information sources, including Markov information sources. And just to start, here are different patterns, and just visually which ones you think they are more complex. So on one hand, we have some regular patterns, and then we could say that they have low information because these regularities make them easy to predict what might be the next symbol. On the other hand, we have some patterns that are more difficult to interpret, in the sense that they might require more information to be described, but then anyway, there are some that have a bit more regularities than others. And the least regularities that you would have, then we could say that would be a random string, that there is absolutely no pattern. And these patterns were generated with elementary cellular automata, which are very simple programs. Actually, let's say we will see one measure of complexity, which is the shortest program that produces an output. So actually, all these programs have the same program producing very different outputs, but then what we are interested is in the shortest program that produces one output. And in this case, the simpler patterns can be shortened in the sense that they don't use explicitly all the information that the more complex patterns are using. Basically, this elementary cellular automata, you have cells in an array, one dimension on the future state of a cell, which will be 0 or 1, black or green, depends on the states of its previous state and its closest neighbors. So 3 inputs, 1 output. The value either 0 or 1 of time t plus 1 depends on the values of 3 cells at time t. And then you have 8 possible combinations, 0, 0, 0, 0, 0, 1, and so on until 1, 1, 1. And you specify those in a lookup table. You have 256 possible rules. And then in that lookup table, just write zeros and ones. And then the number of the rule, it's when you change from base 2, that column to base 10, that's the number of the rule. Actually, there are only 88 equivalent rules, but let's say some of these are ordered, some of these are chaotic, and some of these are complex, and some have non-trivial patterns. So Stephen Wolfram studied these thoroughly in the 80s and 90s, and many people are still studying them. And so-called Wolfram classification that has 4 classes, and actually the first 2 are not different classes, they're the same simple class, class 1. Then the bottom right is class 3, which will be pseudo-random or chaotic patterns. And the bottom left would be class 4 or complex patterns. But then among all the complexity measures that have been proposed, we can have 2 big categories. Some that give you a maximum value when you have random information or random strings. So just like Shannon information, it's maximal for random strings. And then there are others that give you maximum when you have, let's say, a balance between order and chaos. So Kolmogorov complexity, also known as Kolmogorov-Chaitin complexity or logarithmic complexity is the length of the shortest program that produces a string. So it's intuitive in the sense that we might have a long string that looks complicated, but then it might be easy to write a program that produces that string. So then that program actually compresses that string. And then, of course, it depends on the programming language, but usually the Kolmogorov complexity is similar across different languages. A problem is that you cannot compute this complexity because you cannot prove that you have the shortest program. Still, you can approximate it. And this is related to the halting problem that we will see next class. And Chaitin used this same idea, just with a different name, when he was still in high school, to prove that you cannot prove that a number is random. Because if you cannot prove that there will be a shorter program, well, the idea is that if you have a real random number, then the shortest program will be something like print, and then the random number, there will be no shortcut for that. And what Chaitin proved is that you cannot prove that there isn't a shorter program that will produce that random string. So it's one of these paradoxes that you have in computer science, and that's why it cannot be computed, but still it can be approximated. So it's not that it's useless. So, for example, we can see here 4 different strings, and then we can ask ourselves which might have the smallest or largest Kolmogorov complexity. First one will be just xy, 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 and then repeated. So one program that produces this string will be print several times xy, and then it just repeats. So that's a relatively short program. The second string is just print the alphabet. And then, of course, it depends on whether, let's say, if the alphabet is encoded in the program or not. But then if it's part of the program, you're basically writing the whole string. So say every character is different, so it will be difficult to compress. Then the third string, it has some patterns that seem to be repeating, but then there are some variations. So in this case, it's very difficult to generalize and say, you take this pattern and repeat it 3 times, and then you take this other pattern and repeat it 1 time, and then so on. So if you have enough differences, then the shortest program will be just to print out the pattern. And the last one is just print several times 1 character Q. So which one seems to you that you could print with the shortest program, or which one would require the longest program? Yeah, just think about it. So an interesting thing is that if we have a randomly behaving infinite sequence, well, again, theoretical, which will be something like a Markov information source, as we saw last class, the algorithmic complexity per event converges almost always to its entropy rate. So that's a connection with the previous class. And of course, that doesn't hold always, but under certain conditions. A related measure is Bennett's logical depth, which instead of focusing on the shortest program, it focuses on the time it takes to compute a string. So it also considers a shortest program P star. So because of that, it's also not computable. So if we have a shortest program P star that computes a string X on a depth of X to a significance level S, is given by this equation, which is the minimum of TP, which is the number of time steps that the program made on the universal machine to produce X and halt. So if we have this minimum time, then this will be the logical depth. But the idea is that more complex strings would require more computation time. But then, of course, we would need to consider like all possible programs, and we can't do that in theory. In practice, let's say, okay, we'll take lots of programs, and then, especially if we are comparing particular strings, we might be interested simply, okay, for all the programs we have at hand or we can think about, which ones are faster, and then that can give us an approximation of the logical depth. And Sallis entropy, it's a generalization of Shannon entropy information. And Sallis was a Brazilian physicist, recently turned 80. They made a big party. Basically, we have this parameter Q, which will be an exponent. So this is called the entropic index. And the main idea of this entropy is that it can approximate power law distributions. So this, let's say, the Shannon information usually is better for homogeneous distributions or normal distributions. But then for those phenomena that have power law-like distributions, skewed distributions, where you have few states with a high probability and many states with low probability, then Sallis entropy can be used. But then you need to guess or approximate or have some insight on which exponent Q you will use. If you use, if Q tends to 1, then you recover traditional Boltzmann-Gibbs, which is the same as Shannon entropy. Alfred Renyi made a different generalization. Again, recover Shannon information for one of the parameters. So I mean, there are many generalizations of Shannon's entropy. And let me go back a little bit to cybernetics and low regressive variety, which was proposed by Ross Ashby. So in a control system, we have a controller that perceives its environment or that which is trying to control some variables and then acts on that. And that's like a control loop. So Ashby stated, I mean, it's actually more of a tautology, that a successful controller requires to have at least the same variety as that which is trying to control. Basically, if, let's say, a robot is trying to control some industrial scenario, then it should be able to distinguish all the states that the machines that should be controlled by the robot will have access to. And this, of course, is correlated with self-information. So in a sense, variety can be seen as equivalent to information, but in logarithmic scale. Sorry, I mean, variety will be, information will be variety in logarithmic scale. And Yanir Bayam noticed that in many systems, the amount of information or variety necessary to describe a system changes with scale. So, for example, if we have, let's say, 1 cubic meter of a gas, we need lots of information to describe it at the molecular level, because every molecule has a very different momentum and orientation and so on. So we need really lots of information. So something like curve A. So here, the y-axis is the variety, the x-axis is the scale. So for curve A, we have very high variety or information at low scales, which would be something like a gas. But then when you increase the scale, you can average the properties of the gas. And then with very few information, you can describe the system. which would be temperature, pressure, volume, and that's it. Um, Curve V would be more like a ballistic system. It could be something like cubic meter of a comet. And this would require few information at the low scale because there's correlation between the molecules in the sense that they are moving through the solar system together. So if you describe the movement of one of those particles, then you are describing the movement of all of them. And as you increase the scale, you need more or less the same information. And let's say when you go to scales higher than the solar system, then you don't need to describe that anymore. And curve C would be something like a living system where there is certain order at a molecular scale, so you need less information than a gas. But let's say it's, I don't know, a cubic meter of a whale. Then at medium scales, let's say at the scale of meters, then you need much more information to describe how will that matter behave or how that information will behave. And as you go to higher scale, let's say scale of kilometers or thousands of kilometers, then again, you need less information. So all of these measures that I've mentioned so far would belong to the category of more complex is more random. So the higher channel information, the higher the complexity, as understood in this way. And all the rest that I'm going to speak about are more like a balance. And one of these is Fisher information, which under some circumstances can be seen as the derivative of Shannon information, which is basically how much information do we gain when we change a parameter of a system. So let's say if we are changing a parameter and then we plot the Shannon information, if the amount of information that we gain changes a lot, then that gives us a high Fisher information. So it has been found that Fisher information is related to criticality, which is found near phase transitions, usually between order and chaos, so that gives us a certain balance. However, it's like a very sharp transition, so let's say it has its limitations, and also you need to be able to perturb the system in order to measure how information changes. So it's also with not so practical for many cells, for many things. Formally, it's the variance of the score or the expected value of observed information. And measure of complexity that we have proposed with Nelson Fernandez and Carlos Maldonado. It's based on Shannon information. And here, I will not explain what we're plotting here. But, so I mean, it's, these plots are these measures. So the red one will be complexity. And then this K is the connectivity of our random network. And all I need to tell you is that theoretically, there's criticality or phase transition in theory when K equals 2. Because of finite size effects, this is a bit higher. So this measure of complexity correlates with criticality very, very well. And we have used this in many different systems. And this is relevant because many people argue that complexity occurs when we have this balance between order and chaos. So ordered behavior we have for low connectivities in this model, where few change occurs, you have robustness, you have stability, and chaos is when you have fragility, when you have small changes propagate through the whole system. And let's say we can also measure at different scales. So here are different elementary cellular automata. So these are rules belonging to each of the 4 classes proposed by Wolfram. So rule 0, 1, 110, and 30, which would be class 1, 2, 3, and 4. And then here we plot emergence of organization, homeostasis, and complexity at different scales. So basically, if we focus on one cell, uh, and we just measure its information, then that will be scale 1. But then if we take 2 time steps, that gives us 2 bits. So then that would be scale 2. If we take 4 bits, then that would be scale 4, which is what's plotted down here. So here we can see how these different measures change in time. Let me first show the measure, and then we'll go back. So here on the top left is Shannon information. It's the sum of probability times log of the probability. In this example, we just have 2 symbols, 0, 1. So we can normalize it so that this always between 0 and 1. Emergence, we define it as information because one way of understanding emergence is information that's present at one scale and not at another scale. So if we are getting new information, then we can call this emergence. Self-organization can be understood as a reduction in entropy. So 1 minus Shannon information will give you self-organization. And complexity would be their multiplication. So it might sound counterintuitive because many complex systems are at the same time exhibiting emergence and self-organization. However, if we go to an extreme and we want everything to be completely new, so we have always emergence or maximum emergence, then we have randomness, and it's like no pattern is repeated, no regularity, so there's no organization. And then if we go to the extreme of self-organization, then everything is zero. And as we see in this plot, let's say the black curve would be emergence, which is Shannon information. It's a parabola. And then self-organization, it's the blue curve is just flipping it upside down. And then their multiplication is the red curve complexity, which has 2 maxima. So basically, when you have a balance between emergence and self-organization, complexity is maximum. So if we go back here, for random Muller networks, for ordered dynamics, we have low emergence, high self-organization, and then this is the opposite for chaotic regime, and then they are balanced near criticality, which gives us high complexity. I mean, more of this is given in greater detail, including random Muller networks in the modern complexity theoretic course. So if you're interested and can take that course, then you will learn more about that. And we will see also, for example, that if we introduce heterogeneity in complex systems, then the region where you have complexity and actually also anti-fragility broadens. So let's say these curves, if we start introducing different types of heterogeneity, starts becoming broader and broader. So we have more parameters that give complex dynamics. So in this case where we have cellular automata, for example, rule 30, which is chaotic, it has high entropy, information emergence at all the scales, and then rule 110 at low scales, it's almost as high as a random, let's say as a class 3 cellular automaton, which would be chaotic. Then we see that it goes down with scale. And it's the opposite for self-organization. The ordered rules have low entropy, high self-organization, and vice versa. And then for complexity, we see that the order rules, class 1 and 2, and then the chaotic rules, class 3, have low complexity at all scales. And then rule 110 has complexity at at the medium scales. And then if we would increase it properly, this would start going down. But the thing is that this it depends on the period of the ether, which means already getting too technical. But let's say these measures are useful to detect this type of behavior in many different systems. So that's the main message. So let me just close with an example. So I started working on self-organizing traffic lights during my PhD, and then continued with students and colleagues over the years. So traditional traffic lights, it's easy that you will get congestion, and with self-organizing rules where uh, each intersection has sensors and takes local decisions. So actually there's no communication between intersections. They just give preference to the streets with more demand, and let's say they prevent also the blockage of the streets. It's much more efficient. So they just analyzing the statistics. So this is the velocity for different densities. Low density means few cars. High density close to 1, it means that there's no space for vehicles to move on the street. So of course they won't be able to move because simply there's no space. So for the traditional green wave method, which tries to synchronize traffic lights as vehicles move, it's not so good for low densities, and then you have gridlock, and that's it. On the right hand, we have the flow, which is velocity times density. So we see that flow, well, the dashed lines are the optimality curves. So this would be the best you could get in theory. So for low densities, it is optimal. Then these other dotted lines are the phase transitions. Here you have maximum flow for a broad range of densities, and then it starts going down until you have congestion. But then what we did with one master student for his thesis was to measure the complexity of these traffic lights. So if we just look at the intervals of the traffic lights, the green wave, which are regular, they will be maximally organized because it's like just the same period all the time, no emergence, no complexity. And we saw that it's not very good. The self-organizing traffic lights, they have high complexity for many cases, except for when you have medium densities in this phase where you have, let's say, enough demand so that there's always vehicles crossing every intersection. For that region of the parameter space, the best strategy is simply to have a fixed interval. Actually, it doesn't matter whether it's fixed or not. It doesn't matter that much. So in that sense, you have a highly organized regime because let's say they all have the same period. And then for the others, they have high complexity. And then if we look at the measures for the vehicle intervals at an intersection, so we measure how long does it take for a vehicle to cross an intersection, and we see that, let's say, it's regular for the green light methods because, let's say, more or less the traffic has a similar pattern, so the groups of vehicles are more or less the same. So then when there's a vehicle coming, there will be many more vehicles coming behind it. But we can see that the transitions are much smoother for self-organizing traffic lights. Again, there's low complexity for the regime where there's always vehicles crossing at the intersection because it's like perfectly predictable pattern. there's vehicle, 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 and that's it. So the interval between vehicles is the same. Um, so let's say this is not so complex, and let's say where it's more complex is for low densities, where actually the vehicles trigger on demand the traffic lights. And finally, if we look at the vehicle intervals at the streets, now not so much at an intersection, then we see that we have high complexity for most densities, I mean, until gridlock is reached. This gridlock is because of initial conditions, not. So just to conclude, as we have seen in these classes, information allows us to study computation, complexity, and also artificial intelligence. So it's a very valuable tool. This understanding can help us solve all sorts of different problems. We have seen that there's much to do in the sense that we are still understanding what are the implications and limitations of these methods. But since they are practical implications, then we can contribute to improve all sorts of systems. So it's very encouraging to work in this area. So next class, last class, we will see computation, theoretical and practical. So that will be like a wrap-up of information theory, because we can see computation as transformation of information. And if you have any question, please post it in the discussion forums.